1,000 AI agents running a marathon. Once the race starts, almost none of them use AI at all. Hi, welcome back to Hands-on AI. I'm Annie, and I will join by Casey West. Casey West is from Google Cloud, and he led to build this entire agentic system. And what you're looking at right now is 1,000 AI agents running a marathon. It's open source code, and you can check the link on the screen. So each one of them is real and independent. They're all running at the same time. In the last episode, we built the architecture, and today we are going deeper into the decision that making running 1,000 AI agents actually affordable.
So I think, Annie, this is the juicy part. So when do you let an LLM decide and when do you write code? And I think it's one of the more important architectural decisions that we have to make. So if we're back here and we'll go live, because why not? What could happen? What bad could happen in a live demo? But let's go ahead and plan a marathon route. It's actually working. So it's doing what we were discussing earlier. It loaded the GIS spatial engineering skill. It's going to plan a marathon route. This takes a little bit of time, but here we go. So we have a marathon route that gets planned. Cool.
Wow.
And the regular planner agent just outputs this text.
So it's loading a skill that is using a tool, to load the skill. So it has knowledge of GIS spatial engineering, and then it's planning the route to actually planning the route. So, cool.
Yeah, exactly. So here's the route that it planned, right? And interestingly, we had a lot of constraints on how to plan this route. But we knew, for instance, it has to be 26.2 miles long. And it also has to be on a city-approved street network. One of the things that we decided to do here is that this 3D visualization that you see for Las Vegas is very beautiful. However, we couldn't model every single street and every single building in Las Vegas, right? Let me just show you in GitHub because it does a really cool rendering of this.
Wow.
We have a GeoJSON file, and if you go look up GeoJSON, it's a standard. It's a JSON payload that will show coordinates and properties, features, that sort of thing of a map. But you can see here in the blue color that these are all of the roads that are actually available to us to run this marathon route on. Now, again, if you were building a real marathon in Las Vegas, you'd have access to all the roads. But again, we had a limitation. So because of that, if I zoom out again, you can see that we only had a subset of the roads available to us in Las Vegas. So that was one issue that we had. So because of that, we couldn't use Google Maps to just give us a marathon route. The other limitation is that even if we wanted to use Google Maps has two route modes for between destinations that might be interesting. One of them would be cars or driving directions, but driving directions honor things like one-way streets, where if you're running a marathon, you can close the street down and run in whichever direction you want, right? And then if we were going to use walking directions, there's a unique challenge with Las Vegas, which is that walking directions will frequently bring you over bridges, like walking bridges over major roads and through buildings.
Yeah.
Do you remember? So it would be very unlikely that we would build a marathon route that would make you run through the Luxor, for example. The next thing that people were really interested in is, could we just have Gemini build a route for us?
I would rely
based on. Go ahead.
I would have a very smart algorithm to making sure it has an efficient path. This is similar to my interview question to find a route between two different points. And then I think I would rely on the deterministic logic, but I think LLM definitely can give a good route. But if I make a decision, my intuition is more lean towards deterministic logic because it's more reliable and it's give you more optimal solution.
What's funny is not to give too much away about the interview process here at Google, but at least for our role when I'm interviewing, I ask a question about how would you use AI to solve a particular type of problem, and the the best answers are not to go with full large language models in my interview question. And it turns out that's true here as well. So doing a shortest path or a nearest path solution is actually extremely difficult. We would call it an NP hard problem. It's one of the harder problems in computer science. But you can see how noisy this is. And for those of you, and I think Annie, you've probably done this, if you tried to give this to Gemini, it might be able to understand it, but it's going to be very noisy and very difficult for it to like keep track of and keep context of as you add more instructions. But basically there's an algorithm out there called a spine and sprout algorithm. Yeah. So phase one, as I mentioned, is this Dijkstra algorithm that takes the road graph. It uses what's called a Haversine weighted edges to stitch landmarks together. Then phase two is extending the path with a serpentine waypoint. And we use then we also have to, so we do the serpentine waypoint, which will have a series of sequences. And then we have to trim the last segment of those sequences so that we get to exactly 26.2188 miles. That's the specific amount of distance for a marathon officially. So this is deterministic for sure. So building the route itself is deterministic. And very importantly, it's also unit testable. This is all a bunch of gnarly math. So this is why I felt it would be most valuable not to use Gemini and to, in fact, just make this part deterministic, is that all of this is computer science algorithms to solve NP-hard problems that have been built over the last several decades. Now, where I did end up using Gemini is in figuring out which algorithms to use. We used AI Studio because it was just fast enough, but also it was easy enough for us to do two things. So one of them is code execution here. Let me make sure my screen is big enough. So we used AI Studio in this case because I also had non-developers who were also trying to figure out what would the best algorithms be. So what we did is we uploaded, from our files, the network.json file. So that was the GeoJSON file that I showed you earlier with all of those coordinates in it. And then we described in our prompt all of our constraints. And then most importantly, we enabled code execution here. And that allowed us, and we could also do grounding with Google search. So these two things allowed us to have Gemini in AI Studio. Let me just click that button. Gemini in AI Studio was able to look up algorithms for solving problems like this using its search tools and its own knowledge, and then write Python code using code execution that we could use as a starting point.
Wow.
I then took that and I brought it to tools like Gemini CLI, and I said, here's a starting point. Might not be perfect. Here are our constraints. I want this to be unit testable. I want you to do deep code review on this. And we iterated on these algorithms a number of times to get to where we are today.
That is so smart. I will try this way to do research next time. So the routing logic is fully deterministic. But this is the interesting part. Casey still used AI to help choose the deterministic algorithm, just not at runtime. And that is a pattern behind this whole system. We use the model where it actually helps, and we skip the model where it doesn't. They applied that same idea again inside the simulator, and that is where the real trick lives.
So that's how we determined it in the planner agent, right? And then there's two other locations where we had to make similar decisions. The simulator is an agent, but what if the work is really mechanical? But it lives inside of an agent framework. So you still want an agent lifecycle, right? And you still want things like A2A to communicate with it. You still want telemetry, but you don't want an LLM call for something that might be a deterministic or a procedural set of steps. And, you've written a bunch of agents before, Annie, so sometimes you write a bunch of tools that have your deterministic logic in it. And all you really need an agent to do is call tool number 1 and then call tool number 2 and then call tool number 3, right?
Yeah.
Yeah. So the question is do you want an LLM to do that or do you need an LLM to do that?
Depends on the use case. If sometimes for the case that you do not want to add deterministic logic, it's good for LLM to like decide, because sometimes you cannot handle all the cases with different user input. Then I think LLM decide is a good approach, especially cover different edge case. And then if it's a specific use case, for example, I just want a planning, like for example, specific route, I might just want to add deterministic logic to bypass the LLM generation, and I just add some deterministic logic to like force it to do certain thing. And I actually have to do this trick for some of my agent system, that I have to like use callback with before to call to bypass something, and then to do some other deterministic logic in the backend. Yeah. It's like it really depends on use case for my situation. I'm curious for this use case, how do you handle that?
Yeah, so in this use case, the simulator agent's really fascinating because there are a couple of things where we might want the LLM to be a part of decision making, right? Some heuristics, that sort of thing. But to run a simulation is a relatively straightforward approach. You need to set the simulation up, you need to run the simulation itself. And to run the simulation, what we chose is essentially, we call it like server-side ticks, which is a term built from like game development. So like in games, when you have a server, a centralized server, it usually has a tick where every couple of milliseconds or every second, it will essentially try and figure out the state of the entire system, and it keeps track of that state. So that's what we did here as well. So you can think of the simulator as like the game server, and you can think of the runners as little game players that are all running around inside of the game. And so the simulator is trying to figure out, where are all of my runners? What is their current state? What are their properties? So that's what we did here. So here you can see the architecture of the simulator agent. And this is inside of, the agent.py for the simulator. So we still want to use the agent paradigm or the agent's model to organize the complex workflow, but we want to cheat time as much as possible and be as efficient as possible on the execution. So if we go down to pre-agent, see pre-race agent here, this is the trick. So pre-race agent and the tick agent are both LLM agents, and they have a model. But if we look at line 252, you can see in this comment here, the model is required by the LLM agent in order to create the object, but it's never actually called, because the before model callback, this is an ADK feature of callbacks. The before model callback intercepts every invocation and returns deterministic tool calls. So in this case, the pre-race thing just needs to set up and call a couple of tools in order to set up the environment.
Wow.
I knew it needed to do the same thing every time, but I still wanted to have it function exactly like any other ADK agent. So I could get the lifecycle management, I could hook into the callbacks, I could get the telemetry, all that stuff.
Wow. So before you even using the model, you have this callback, intercept this lifecycle, and then just switch to your deterministic logic to bypass the actual LLM use.
That's right.
That's so cool.
And this is important. It saves money, it reduces latency, and it guarantees reliability in a part of the agent system where we actually need it.
I did a similar thing with one of my Gemini live agent, that, when in the voice context, if you have a live agent, like have voice in, voice out, with tool call, add latency, so that the voice is not as fast as not using tool call. So I basically also use it before tool callback to bypass the tool call so that it will return to me immediately.
I'm also still adhering to the ADK paradigm. Function call will still set up a tool call using ADK's own client libraries and publicly, provided interfaces to do the exact same thing. And we can even set session state, context state, that sort of thing here. And that's exactly how this works.
Wow.
Yeah. So, and it's the same thing in the ticks. So I mentioned the ticks as well. If I scroll down a little bit here, like we can see the tick callback does the same thing. the tick callback only ever needs to call advance tick and check if the race is complete. And because I know that that's all it has to do, I want to cut down on any latency. I don't need the LLM calls. And just because of the runners especially, and because of all of the things that are happening when we run the simulation, there's already a huge amount of context and like messages being passed to Gemini. So any places where we can optimize it, this cut down on the time and space. So this is a really efficient model where you do have some areas in a code base where you know they need to be deterministic. You can get away with that even within a framework like ADK and still adhere to ADK and get all of the features that are available to you. It would be easy to write this where you short circuit like tool calling and your callback does all the work by itself, but then you lose things like visibility and telemetry. So I would recommend to anyone out there, if you feel like you need to do a similar thing, use a model like this and tear apart this code base and steal it for yourself.
That is so cool. So I feel like it's a agent surface, but below the surface it's the deterministic normal, like deterministic logic, deterministic code. Do you think it's still an agent?
Yes. So the simulator agent is our most sophisticated. Like it's in ADK, we would call it a multi-agent system, even though this whole thing is like many independent agents that are like network disconnected from one another. The simulator agent actually has, in ADK, we call them workflow agents. So it uses a looping agent, it uses a sequential agent, things like that. So it is a multi-agent architecture with sub-agents. So I still think it's an agent, even if some pieces are deterministic.
Yeah, this is really cool because I've been struggling a lot with how do you build a hybrid system while you still keep the advantages of agent system, but also adding more control and basically have a good balance of use determinist logic when it needs to, but rely on AI for when AI is doing the better. When it's a time for AI to doing a better job. So how do you build a hybrid system? I think this is a really cool way for us to, first, we have all the benefit of ADK agents. We have benefit of life cycle, this tool call, with telemetry, observability, and more. But at the same time, we can adding deterministic logic bypass the model callback. It's really cool demonstration of how you can build a hybrid system, how you can really have a good balance of both. It's really cool.
Yeah, thank you. We did the same thing with runners, just briefly. So the runner agent uses an LLM, but the runners we have a lot of them. That's our most scalable agent in terms of how many we're trying to run or simulate at the same time.
Yeah.
And any latency is going to be a problem. So we also built what we called the Autopilot runner, which you can see on screen here. Mm-hmm. And it just extends or augments the behavior of the regular runner agent. So that's what get base agent does here. But then instead of calling the LLM, it makes its own decisions using some heuristics and a bunch of data that we pulled from Gemini Deep Research about how runners behave. So it's all code based, but that allows the autopilot agents to run within milliseconds whenever they get called. And that's how we could get the back end can support up to 10,000 simultaneous agents. The front end is this very beautiful 3-dimensional visualization, and it's constrained by Chrome and memory management, CPU and GPU. So we were only able to show 1,000 on the screen during the demo, but that's how we got to that scale.
Cool. So you talk about you're showing 1,000 agent session at the same time. And I know that now we cover, we understand architecture, we are deep dive into the agent code, we understanding how it loading the skill, and we're understanding how to balance the LLM and the deterministic logic. But still, what is the real magic behind the scene so that all the 1,000 sessions can run at the same time? What is the trick?
Yeah, that's a great question. So I think to do that, I want to just dive in a little bit to things like the agent lifecycle so we can see how things work. So what we're looking at right here is one of the developer tool UIs that we built into Race Condition. It's the agent telemetry dashboard. And we can see actually some messages that are coming in right now. And what you're watching is every row is a real ADK lifecycle event from a real agent session. And we have rows that say like starting and finished, or model start, model end, that kind of thing. And we also have them grouped by session IDs and the sequence of the message within that session. So this is pretty cool. I think a thing to know is that all of these are also messages that are passed over the gateway using PubSub as a broadcasting mechanism, and then get emitted over a WebSocket to this front end UI. So if I click run simulation now, this is live. We should hopefully see messages. Yeah, so the user said run a simulation, right? That was me. So that's what we're doing there. And now we can see that the planner with eval is doing a lot of the heavy lifting right now. It'll be interesting to see how fast this is, considering, Gemini latency and API calls and all of that. But now we can see actually a number of agents that are running, including these runner autopilots. So they all got messages. Let me see if I can scroll to like tool end from process tick. So the simulator agent has a sub agent that is a tick processor, right? So it sends a process tick message event to the runner autopilot agent. And we've already scrolled past it here. We can see this is how many events are running in the system live. And we can see things like latency and total events here, total number of tokens. So Gemini 3 Flash Preview has 350,000 tokens. So as you can see, this is a decent amount of work, right?
So you're looking at about 350,000 tokens, and that is not zero. But here is the key. Those tokens are not from the route math. The route math is deterministic code. So that part is basically free. The token comes from the AI doing judgment. Which landmarks should we include? Does the timing make sense? Is the plan safe and runnable? The model reasons through that once, and then before the race. And then 1,000 runners just take over. And they actually never call the model itself. So adding more runners does not add more tokens. The AI decides and the code runs.
So this is the fire hose of everything that's happening in the system. And with 1,000 runner agents, it means that we've got these 1,000 independent ADK sessions, each one with its own state, right? And we happen to be running this on Cloud Run, but these processes are stateless. And we have, to run the real system in production, we had over 50 instances of the service for runner autopilot on Cloud Run. So that's 50, unique server processes that are running on Cloud Run, all stateless. So session state has to live somewhere, and it has to be shared, because these runners are keeping track of the sessions throughout the history. You can see that this is the 67th turn on this session for this runner. This is one unique runner. And really, that was one of the first things that broke for us. So when you're building a scale for stateless sessions where you have to do large scale, one of the first questions is, where does the state live? I think we have to talk a little bit about ADK and session stores. So ADK by default comes with a handful of session stores automatically available. Andy, do you know which session store, when you're running ADK locally and you're just developing your own agent, which session store it uses by default?
Yeah, so ADK has in-memory session service, basically using the RAM, and it also have the option like database session service. You can use your own database solution, for example, AlloDB or SQLite, Cloud SQL, stuff like that. And then there's also option called Redis AI Session Service. You can using our agent runtime. I'm gonna pass it back to you, Casey. So how the system using memory? How does the session service configure here?
Yeah, exactly. So first of all, very thorough response. I love that. And you're right. So we had a couple of challenges with the default options that were available to us in ADK. In memory doesn't work when you have multiple instances of your agent running at the same time, like 50 instances on Cloud Run. because then your session state is only localized to a single instance. And I needed to share the session state across all those instances because we never know which one the global load balancer will give the next message to. But I also couldn't use the, what do we call it now? The agent platform sessions in Gemini Enterprise Agent Platform, because this agent was running on Cloud Run instead of running in agent runtime. And it was running on Cloud Run so I could get the scalable characteristics I needed.
Yeah, but I could, right?
What's that?
But it takes time to loading this, right? I think the run
right, so
faster.
Yeah, so the third option, of course, would be like a database like AlloyDB, and I did try that, but the overhead of the SQL calls, the queries to retrieve and store session state and the transactions that were required were actually too slow, and they became one of the bottlenecks. So I had to come up with a creative workaround. So one of the techniques I was using in this architecture already to try and keep things fast and with really low latency was using Google Cloud's memory store, which is managed Redis. And so my question was, could I use Redis as a session store? Well, ADK doesn't have that by default. But what I found that I really was very happy about is that there is a repo that Google maintains with community contributions called Google ADK Community. You can find it on GitHub. And in Google ADK Community is a Redis session service that a community member had written. Wow. So I used it. And then my agents were as fast as I needed them to be. So that was one of the key things that I was able to do.
Kudos to that community contributor.
Yeah, exactly. I was really, really, really pleased with that. And then just to give them like a shout out here, all you have to do in your Python code is pull in the Google ADK community repo, and then you can configure your session service. In this case, the Redis session service in my repo is a subclass that does a few extra tweaks just for a little bit of additional performance, which is that it prunes events and prevents blob growth. So just making sure that we keep everything as streamlined as possible, because again, I have 1,000 simultaneous sessions. We send them all a message over PubSub instantly and get all the responses back, and we have to collect them as fast as possible. There's way more to go into with this, and there's maybe not enough time, but that's where I will encourage everybody to explore this code base. And let me actually just share with the community, everybody who's listening, one of the ways you can share that you can explore this code base, whether you're using things like Claude Code, Cursor, or like Gemini CLI, is that it includes skills for your AI harnesses or AI dev tools, including and exploring the code base skill, which will explain to your AI coding assistant like Gemini CLI how to look into this code base, where things are. And then you can ask a question like, how did we get a highly efficient Redis session service for extremely low latency, scalable sessions with agents?
Wow. No wonder when I studied this repo, my AI is really efficient with all the answers.
Yeah.
Oh, thanks for, creating those skills. That's pretty helpful. Thank you for this great session, Casey. I've learned so much from this conversation.
Thank you.
And
I had so much fun exploring it with you again.
Stay tuned, and we'll have more episodes coming up. And again, thank you so much for watching this, and I'll see you next time. And bye.
Bye.